probability time now, and we're going to discuss the Bernoulli distribution, which came from a mathematician back in the second half of the 1600s, Jacob Bernoulli. And he did all of his work in Switzerland in the second half of the 1600s. In this video we're going to look at two goals, and first learning goal is we're going to know the background for what makes a Bernoulli distribution different to other things, and we're going to identify contexts where it is suitable for using the Bernoulli distribution and what's called the Bernoulli random variable. The Bernoulli random variable. We're going to look at what situations or contexts would lend themselves to be suitable as a place where Bernoulli distribution or the Bernoulli random variable is used for modeling. The Bernoulli random variable, I'll just call it the BRV. That's nothing official, it just saves me having to write it. The Bernoulli random variable is the simplest kind of random variable. It only has two values associated with it, that's 0 and 1. Let me explain that a little bit. We might see some notation like this, for example, and where we've got these big P's and little p's, and hopefully you've already looked at some discrete probability distributions and discrete random variables and all that, because this is in the area of discrete probability. And you might have seen notation a bit like that last time, and the little p is the probability of what's called a success, so-called success, but it's defined to be anything you like within certain parameters. And that there is the complement of that, so that's the probability of a failure. Alright, the complement, 1 minus a probability gives the complement, and that would be the probability of what's called a failure. And you can see the two values that I said before, 0 and 1 here. So this means basically for one trial at a time we look at the probabilities. So this notation is discussing or it is describing the probability of success on a single trial, one by one. Okay, that's an important point. On each trial taken one at a time. Okay, on a single trial. Okay, so one at a time. Some illustrative examples which will no doubt help. Things like win-lose. They won the election, they lost the election if it's a case of win-lose. A baby being born, biologically male or female. Maybe it's the response to something like a like, not like, whether it's social media or a movie or something. On a die, on a fair six-sided die, you can have getting a 3 versus not 3, even though there are 6 sides on such a dice. 3 not 3, it can be defined that way. Okay, and for a coin flip, heads or tails on a fair coin, so heads, tails would be the two outcomes there. And so for that one, that's an easy one, little p, the probability of success. Let's say we're looking at getting a tail. The probability of success for the tail for each trial, one trial. Alright, once again that's one at a time. One trial is 0.5. We know that. The one before it, getting a 3, probability of a success there is 1/6. Okay, these other ones could have such probabilities associated with them, but they may have to be given to you in the question. If we're looking at female babies born, for example, in this one here, it might be something close to 0.5, but looking at tables of large-scale data, perhaps it's not exactly 0.5. We're looking at representing success or failure on a single Bernoulli trial, and we have to define what a Bernoulli trial is, which makes sense. Okay, the conditions that must be adhered to be called a Bernoulli trial for a given event, we're only looking at success and fail. There's no third option there. Okay, so success is getting the outcome you're looking for and fail is not. And as a corollary to that, it makes sense that the probability of a success plus the probability of a fail equal 1, which is the whole sample space. And these probabilities of a success and a fail, they're constant, they stay constant. They don't go varying in the middle of a task, they stay constant. And we're talking about successive trials being independent. Successive trials are independent, so one doesn't affect the next one. Okay? And we look at some of the examples above, like the coin flip, too, they are independent. Okay, previous trial does not affect the next one. The next video will build on this, and it'll look at using Bernoulli random variables as a model for two outcome type situations. So we're going to do a bit more maths in the next one.